Okay, in your table of contents on page 25 we have quadratic part 2, and on the worksheet it'll say quadratic notes number 2 as well. And we're going to start this out like we have before. We got to answer, is this linear quadratic? Remember, it is quadratic because it has that little square on our problem. We're going to type this in our calculator. 1 divided by 9x squared minus 16 is one way I can do this. Or realize you could do your fraction, that is 1 over 9 x squared minus 16. Either one of those will work for the problems that we have here. Okay. Alright, I'm going to turn that graph off for now. I'm going to go to the table. And remember, we got to fill in our table based on our data that we have in our charts. So I'm looking for the vertex and realize this is at a 16. So that means I should be close to a 16 in my chart. If I look at my 16, notice that have 15.89, 15.89 is above and below, 15.56, 15.56 are above and below, but the 16 is not repeating, so that means the 16 is my vertex point, like what we've been doing. So I'm going to start with 0, 16 in the middle, and remember, I don't want decimals, so I do see that I have 3 and negative 15 at the bottom and at the top, so those will be my next points. And then I need to stretch up one more and find the next whole number. There it is, negative 6 and negative 12. And that should match on the bottom at 6. There it is, 6 and negative 12. So that I have the mirror image. Remember, that represents my vertex of my problem. Very, very important number. I need to graph this picture now. So I'm going to do 0 and negative 16. It's way down there on my graph. The next one is 3 and negative 15. Five, 6 and negative 12. So I can see my graph is going to be going in this fashion from both directions. Very, very wide graph. Okay, that means my domain, as you have seen, is all real numbers, but the range, this point down here at the bottom is very, very crucial. Remember, it pertains to your vertex because I know that it was at negative 16. So that is my other number, and then the graph is above it, so make sure you use the greater than or equal to symbol to represent the range for this particular graph that we have. Once you describe the line formed, is it a straight line or a parabola? Well, this is curved graph, so that means this is a parabola. And concavity, that's a new one that you didn't have before, but this is like concave lenses that you have in science. Concavity is talking about whether this graph is going concave up or concave down, and if you're looking at this particular graph, this one is going up in that particular fashion, and the one you had on the previous notes, if you look at it, it was curving down. That would be concave down, and this one would be concave up. And one way is to look at where your arrows are. This one's pointing up, therefore it's concave up. These arrows were pointing down, therefore it would be labeled as concave down. Okay, vertex point is what you had before, so we know that is 0 and negative 16. Make sure you put that in parentheses because it does say the word point. And then, is this vertex point a maximum or minimum point? Well, this is the lowest part of my graph, therefore that is the minimum. And it says, what is the axis of symmetry? Well, if I'm drawing my axis of symmetry, let me find a straight edge somewhere. I'm going to use a highlighter because it's easier to see. I recommend you do the same thing. I want to actually draw the axis of symmetry on my picture, because that is number 10. And remember, the axis of symmetry is where this is cutting your picture exactly in half, And for now, this is always going to be on x equals 0 until we start moving it away from the y-axis. This is always at that value. And it says graph it. I already did number 10 when I highlighted that. So make sure you are making that a dark, bold line on your graphs, or you are highlighting it so we can see where you're actually drawing the axis of symmetry. And then it says, what is the parent graph? Remember, that one was the basic graph. That was y equals x squared. Now, they want us to graph the parent graph. Now, the coordinates, when we graph this, remember, there are going to be 5 coordinates here. We're going to start out at 0, 0. But we've got to go to the left and to the right. So I'm going to use 1 and 2, and then 2 and 4. Oh, I'm sorry, not 1 and 2. That'd be 1, 1, and 2, 4. And then likewise in the opposite direction, that'd be negative 1, 1, and then negative 2, 4. Are the coordinates that you're going to use for this parent graph. Realize that's just plugging in your values. 1 and 1 squared is 1. If you plug in a 2, 2 squared is 4. Plug in a 0, 0 squared is 0. That's just where I'm getting my points. So I'm going to graph those points on my picture. Okay, and there's a really small little graph there compared to the one that I have down below for graphing the parent graph, and that's what this one represents, is your parent graph. Okay. Number 13, very important question. So describe the graph compared to this parent graph. Alright, the graph of the parabola, is it stretched or compressed? If I'm comparing the parent graph to the next one, you got to interpret these two words, stretched or compressed. Stretching is like a rubber band. Let me see if I can find one real quick. Okay, here we go. Alright, here is a kind of a rubber band to show you what I'm talking about here. When you have a rubber band and you stretch it, it gets real narrow and skinny. See how close the sides get together? Really narrow and skinny. But when I compress it means to squeeze it together, to shrink it down. When I start pushing together, you see how it widens out and it gets flat? Kind of fat and flat. It widens out in this place. So if I'm stretching, it's getting really, really narrow, and if I'm compressing, it's flattening out and getting wide for this aspect here. Okay? So if I look at the parent graph to this graph, the parent graph is the normal one. It's the perfect graph. And as it gets more and more stretched, it's getting skinnier and skinnier. It's getting really, really narrow. And if I look at this graph, if I was to slide it down here to get it to go out, means that I'm having to push this down to get it to kind of model this particular picture. Well, when I'm having to push it down, that means I'm having to compress this down. I'm compressing it to get it smaller. And that means the edges start flattening out and getting wide to form this graph. But as I stretch it, that would be a skinny one. One way of looking at it, to relate to what you've been doing before, I was telling you guys that when we described this A value was looking at your slope. Well, on these particular equations, we don't have a slope, but you do have an x squared. And that number that's in front of your x squared, that is actually called an A. And if this A, once again, it's treated almost the same thing as slope, but because this is quadratic, they changed it to the letter A. If A is greater than 1, then that means it is stretching. If the A is less than 1, then it is compressing. And if A equals 1, then it's just the same. I need a same on here. Didn't change at all. If I'm looking at my equation, here I have 1 over 9. If I actually divide 1 over 9 in my calculator, I see that is actually like 0.111111. That is actually smaller than 1. That means this is compressing, and that models with the rubber band because I was having to push it down to get it to widen out and get fatter and wider for my rubber band. That means this is compressed. Now the B option, this is still your y-intercept. You're still looking at where it is crossing, and that is still modeled in your graph, which is also modeled by your vertex on these problems only. If I look at where it starts, it goes down 16. So this will be 16 units down. But you're looking at your y-intercept. Where is it crossing the y-axis? Alright, I'll see you in class.